Now let's put some of this together in an example. We're going to find the zeros of this polynomial, 3x cubed minus 10x squared plus or minus 23x minus 10. But before we find them, let's think about what we could expect to find. There must be 3 zeros, counting multiplicity, because the degree is 3. There's one sign change. The coefficients are positive, negative, negative, negative. So Descartes' rule of signs tells us there must be one positive real zero. So 3 zeros altogether. One of them is a positive real number, and then the other 2 would have to be either negative real numbers or non-real numbers involving I. And the possible rational zeros, they have to be a factor of the constant term over a factor of the leading coefficient. So that means the possibilities are positive or negative 1, 2, 5, 10, 1/3, 2/3, 5/3, or 10/3. So now that we have some idea what might work, let's try one of these. If we try one by setting up synthetic division with the 3, negative 10, negative 23, negative 10, and 1 out in front, bring down the 3. 1 times 3 is 3. Negative 10 plus 3 is negative 7. 1 times negative 7 is negative 7. Negative 23 plus negative 7 is negative 30. 1 times negative 30 is negative 30. And negative 10 plus negative 30 is negative 40. So we didn't get 0, which means that 1 is not a zero of this polynomial. Oh well, there's still plenty of other things we can try. Let's try 2. Putting the 2 out in front, bring down the 3. 2 times 3 is 6. Negative 10 plus 6 is negative 4. 2 times negative 4 is negative 8. Add negative 23 plus negative 8 to get negative 31. 2 times negative 31 is negative 62. Negative 10 plus negative 62 is negative 72. And fail. 2 is not a zero. Oh well, let's try 5. Bring down the 3. 5 times 3 is 15. Negative 10 plus 15 is 5. 5 times 5 is 25. Negative 23 plus 25 is 2. 5 times 2 is 10. Negative 10 plus 10 is 0. So that one worked. 5 is a zero of this polynomial. And once we have one thing that does work, so that the synthetic division did come out even, that tells us that we can take our original polynomial and break it up into what we divided by, which was x minus 5, times what we got as the quotient, which was 3x squared plus 5x plus 2. And now, to take it the rest of the way, we just have to break up the 3x squared plus 5x plus 2, but we can factor that the old-fashioned way, the way we've been factoring things for a long time now. Just figure out how to break it up so that when you multiply it together, you get this. We need a 3x times x to get 3x squared. The numbers on the end have to multiply to give you 2, and the outside plus the inside have to add up to 5x. So the correct factors are 3x plus 2 times x plus 1. And to know when the whole thing is equal to 0, well, that would just be when any one of the individual factors is equal to 0. X minus 5 could equal 0, which means x equals 5, so that is a 0. 3x plus 2 could equal 0, so 3x equals negative 2, so x equals negative 2/3. Or x plus 1 could equal 0, so x could equal negative 1. So it turns out we found the 3 zeros. They are 5, negative 2/3, and negative 1. Now, if you have a graphing calculator or a graphing program, you could have maybe saved yourself a little work by asking it to graph this function for you. And then remember that the real number zeros of a polynomial show up on the graph as x-intercepts. So looking at this graph on the graphing calculator, I can see it doesn't look like there's an x-intercept at 1 or at 2, but it does look like there's one at 5. And then there's a couple more over here at negative something. Turned out to be negative 2/3 and negative 1. So just from looking at the graph, I can't tell whether those are like exactly 5 or just something really close to it, but at least that gives me a good idea that either 5 or something close to it is a 0. So when I know what to try and what not to try, I can try 5. Let's try this one. Find all solutions to the equation 3x cubed plus 23x squared plus 40x minus 16 equals 0. Let's start by figuring out what we know about the solutions. Solutions to the equation are the same as zeros of the polynomial, and it's a degree 3 polynomial, so we are expecting to find 3 zeros, counting multiplicity. How many sign changes? Positive, 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 negative, 1 sign change. So Descartes' rule of signs tells us there must be 1 positive real zero. The other 2 are either negative or non-real complex numbers. The possibilities for rational zeros are they have to be a factor of 16 over a factor of 3. So it could be positive or negative 1, 2, 4, 8, 16, any of those just over 1, or any of those over 3. Okay, let's try one of those. If we try 1, set up the synthetic division with the 3, 23, 40, negative 16, and the 1 out in front. Bring down the 3. 1 times 3 is 3. 23 plus 3 is 26. 1 times 26 is 26. 40 plus 26 is 66. 1 times 66 is 66. Negative 16 plus 66 is 50. Okay, 1 is not a 0. But there's also something else that I've learned from doing this. Notice that all the numbers in the bottom row turned out to be positive. Positive 3, positive 26, positive 66, positive 50 for a remainder. And that tells me that not only is 1 not a 0, but there can't be any zeros that are any bigger than 1. There can't be any zeros greater than 1 either. Why? Well, when we divided by x minus 1 and got a quotient of 3x squared plus 26 plus 60 plus 26x plus 66 and a remainder of 50, that means that the big polynomial that we started with can be broken up into x minus 1, what we divided by, times 3x squared plus 26x plus 66, what we got as a quotient, plus the 50 that we got for a remainder. And now, if you plug in any number greater than 1 for x, if the number you put in for x is anything bigger than 1, then x minus 1 is going to be positive. Something bigger than 1 minus 1 is positive. And the x squared and the x and all of this is going to be positive. 3x squared plus 26x plus 66 has to come out positive because the number you're plugging in for x is positive. So we have a positive times a positive plus 50, which makes it even bigger. That's got to come out to be positive. There's no way that can come out to equal 0 if what we plug in for x is bigger than 1. So if we're looking for something that we can plug in that will make this come out to be 0, well, we can rule out anything greater than 1. We got to think of numbers that are less than 1 or possibly complex numbers. And the rule that we're using here goes like this. Suppose you're using synthetic division to divide a polynomial by x minus some number. If that number is positive, like it was in this last example, it was positive 1. If that number is positive, and all the numbers you get on the bottom row of the synthetic division come out all positive, you can conclude that your polynomial has no real zeros greater than the number you tried. There's another half to this, and it goes if, that should be a C, sorry, if C is negative, and the numbers on the bottom row of the synthetic division alternate signs, like they go positive, negative, then you can conclude that your polynomial has no real zeros less than the number you tried. So this is not something that you have to know about or have to use, but if you do know about it, and this kind of situation does happen to come up, it can give you a little bonus information about what your zeros might or might not or couldn't be. Okay, back to the problem we're solving. We tried 1, it didn't work. It told us that 1 was an upper bound on the solutions. There couldn't be any that are any bigger than 1. So let's try something that isn't bigger than 1. So one of the possibilities on our list that was positive, but it wasn't bigger than 1, was 1/3. Let's try that. Put a 1/3 out in front, bring down the 3. 1/3 times 3 is 1. 23 plus 1 is 24. 1/3 of 24 is 8. 40 plus 8 is 48. 1/3 of 48 is 16. And negative 16 plus 16 is 0. Victory. We found something that works. And that tells us we can factor this into x minus 1/3 times the quotient 3x squared plus 24x plus 48. Now let's see if we can finish factoring that. One thing we could do is pull out a common factor of 3. When you pull that out, you get 3 times x squared plus 8x plus 16. And then that x squared plus 8x plus 16 breaks up into x plus 4 times x plus 4. Or if you want, you can write that as x plus 4 squared. So we have 3 times x minus 1/3 times x plus 4 squared, 2 of those. So the zeros of that polynomial, or the solutions to that equation, are 1/3 and -4 with multiplicity 2. So we didn't get 3 different solutions, but counting multiplicity, we did get 3 solutions. The positive number 1/3, and then the 2 -4s.